Hi everyone, this is Hal Tasaki. In this video, I'd like to discuss my latest work. The ground state of the spin 1 antiferromagnetic Heisenberg chain is topologically non-trivial. It would be wonderful if this were the title, but actually I have to add an assumption if gapped. But even with this assumption, I believe that the result is important and interesting. So let's get started. The spin 1 antiferromagnetic Heisenberg chain with this Hamiltonian may have either a unique gap ground state that is topologically trivial, or a unique gap ground state that is topologically non-trivial, or gapless or degenerate ground states. This statement is trivial because the list is exhaustive. And people believe that the second possibility is the case, but nobody has proved it. And in this work, I rigorously ruled out this first possibility. So the second and the third possibilities remain, and of course, this is not yet complete. But let me stress that this is very likely to be the first rigorous and non-trivial result about the ground state of the spin 1 antiferromagnetic Heisenberg chain. This is my table of contents, and I like to discuss introduction motivation rather carefully. Let's discuss the ground state of the general spin S antiferromagnetic Heisenberg chain with this Hamiltonian. Back in 1980s, Duncan Haldane made a very interesting discovery that the nature of the ground state and low-lying state of this model depends on whether S is a half-odd integer or an integer. When S is a half-odd integer like 1/2, 3/2, he argued that the model has a unique gapless ground state. And when S is an integer like 1, 2, the model has a unique gapped ground state. So this is the spectrum. In this case, this is the ground state energy. There is a gap, which is now called the Haldane gap, and there are a bunch of excited energies. Okay, this is very interesting, but this was not the end of the story. People then discovered the picture of symmetry-protected topological phases, SPT phases. And now we know that this integer S case is further divided into two classes. And when S is even, then the ground state of this model belongs to a trivial SPT phase. When S is odd, like 1, 3, the ground state belongs to a non-trivial SPT phase. Okay, what do I mean by non-trivial SPT phase? Well, let's consider the spin 1 case. And this is the antiferromagnetic Heisenberg chain Hamiltonian, and we believe nobody has proved it, but we believe that it has a unique gapped ground state. It means a unique ground state accompanied by a finite energy gap. Okay, and let's consider this trivial model whose Hamiltonian is simply the sum of SZ squared. Okay, so this is spin 1 model, so basis states that each site is plus 0 minus, and SZ acts on these basis states like this. Then it is immediately clear that the unique ground state of this Hamiltonian is simply the simple tensor product of all zeros. And the ground state energy is 0. And if you have like 1 plus, then you get 1 extra energy 1. So it has an energy gap 1. Okay. So we have two models of spin 1 chain with unique gap ground states. So why don't we consider a model that interpolates these two Hamiltonians? So this is just a simple interpolating Hamiltonian where S is a parameter between 0 and 1. And of course, you can never solve this. So let's look at the energy gap of this model numerically. So this is a plot of energy gap, which means the difference between the first excited energy and the ground state energy. This is a gap for various values of S and for finite chains. And so this there is a result for finite chains with lengths 4, 6, 8, up to 18. And this beautiful plot was done by my young friend Emil. Okay. And first of all, when S equals 0, we have this trivial model, and it has this trivial energy gap 1, as I discussed before. And when S equals 1, this is the antiferromagnetic Heisenberg chain. And you see that the energy gap is going down as system size increases, and it's sort of converging to somewhere here, like 0.4. And this is nothing but the Haldane gap. But you also see that it's going down, and it is very likely that here we have a gapless point. So there seems to be a phase transition in this interpolating model. And in fact, one of the main result of this work is that we rigorously prove without any assumptions that there is a certain phase transition between H0 and H1 in this interpolating model. Okay, anyway, let's continue. So this is the interpolating model, and this is the expected phase diagram. I said there must be a gapless critical point here, so there are two phases, but both phases have unique gap ground states, and there are no symmetry breaking. So you cannot distinguish between these two phases by a standard order parameter. Okay. But now we understand that these two phases are distinct symmetry-protected topological phases, SPT phases. And since this phase contains this trivial model, so this is called the trivial SPT phase, and this one is called non-trivial SPT phase. And I'm not going into detail, but it is believed that there is always a phase transition if the interpolating Hamiltonian, not only this one, have one of the following symmetries. Okay, and actually in this case, this Hamiltonian has all the four symmetries. Okay, let's continue. So this is a phase diagram, and I said that you cannot distinguish between these two phases by an order parameter, but you can distinguish, the two phases are distinguished by something called topological index. Okay, and topological index is defined for a locally unique gap ground state on the infinite chain, and it is invariant under a smooth modification of the model if you keep this symmetry. Okay, and so the essential step in the research of SPT phases is to define proper indices. And it was done for matrix product states by Pullman, Turner, Belk, and Noshikawa. And it was extended to general unique gap ground states by Yoshiko Ogata. Okay, what about examples? If you, for example, compute this index in the ground state of this trivial model, H0, and then you get index 1. And there is something called the AKLT model, which is a prototypical solvable model in the Haldane phase. And if you compute the index in this AKLT ground state, you get -1. Okay, so it's working, it's perfect. So this is a rough summary. We have a general picture of SPT phases, and we have well-defined indices, and there's also index theorem. And as for example, the AKLT model provides a rigorous example of everything. So everything fits nicely, but I have to stress that nothing rigorous had been proved about the antiferromagnetic Heisenberg chain with odd S. And this is the most standard model, and this was where everything started. Okay, so this motivates my work. And the goal of the present work is this. So there are two conjectures about the spin 1 antiferromagnetic Heisenberg chain. Number one, it has a unique gap ground state. So this is nothing but the Haldane conjecture. And number two is that this model belongs to a non-trivial SPT phase. So in this work, I will assume number one. I will assume Haldane conjecture. Okay, of course I want to prove one, but it looks very, very difficult for the moment, so I will assume it. But with this assumption, I rigorously justify number two. Okay, and actually I have been thinking about this problem for quite a long time, at least for like 5 or 6 years, and I thought that it would be very difficult to prove this, and I needed some new technique. But finally, it turned out that the proof is quite elementary, and I only use standard leap Matisse type technique and elementary index theorem defined by myself. Okay, and I also note that I will concentrate on the spin 1 case, but the discussion just readily extends to general odd S case. Okay, so let me discuss main results of the present paper. So I concentrate on the spin 1 model, and I want to treat the model on infinite chain, but first I look at the model on a finite open chain with odd number of sites, and consider this Hamiltonian. This is essentially the antiferromagnetic Heisenberg model Hamiltonian, but I add this magnetic field at the two ends of the chain, okay, at the two edges. And then this is a remark for an expert. If you look at the symmetry, then all these standard three symmetries are broken by this external magnetic field. But still, this fourth symmetry discovered by Yohei Fuji, Frank Pullman, and Masaki Yoshikawa survives. I call it U1 cross Z2 symmetry, and it's a symmetry with respect to any rotation about the z-axis, any spin rotation about the z-axis, and the inversion about the origin. Okay. Anyway, so I consider this Hamiltonian for a finite chain, and then this is an elementary lemma which can be proved by very standard technique that you can find in textbooks, including my textbook, my book. And what you can prove is this. This Hamiltonian has a unique ground state. Of course, L is finite. So on finite chain, this finite chain Hamiltonian HL has a unique ground state, and it satisfies this. So this is a total SZ operator. So this means that the total SZ in this ground state is exactly 1. Okay. And then here comes the assumption, the essential assumption. So let E ground state and E first be the ground state and the first excited energies. Okay. And we know that they are different because the ground state is unique. But here is much stronger assumption. Okay. I assume that there are constants H, gamma, and L0 such that this energy gap for a finite system is lower bounded by gamma uniformly for any sufficiently large L. Okay. And I will say that this is highly non-trivial, probably very difficult, and still not proved. Okay. And there are many techniques for proving the existence of finite energy gap in infinite chain, but none of them still works for this model. But I think we have to try proving this. But anyway, this is an assumption here, and it is of course expected that this is true with gamma about 0.4. This is the Haldane gap and some modest value of external magnetic field. Okay, and I stress that this H magnetic field is necessary because without H, it is known that this model has low lying almost gapless excitation, which is located at the edge, at the two edges of the chain. Okay, so this one is really necessary. Okay, so with this result, with this assumption, this is our main theorem. And before that, I want to define the ground state for the infinite chain. So okay, so here this is phi L. This is finite volume ground state, and so this is the standard ground state expectation value of any local operator A. And then I just take the limit in which L goes to infinity. If necessary, you take a subsequence, and then you get this limit. And this limit defines a locally unique gap ground state of infinite chain Hamiltonian. Okay, and then the main theorem, the main result is that the index of this infinite volume ground state is -1. And this index is the one defined by myself. I will explain later. And let's by omega s, I denote the ground state, the infinite volume ground state of this interpolating Hamiltonian HS. And then it is very, very easily found that the index of omega 0 is 1. Okay, so they are different. Then from the index theorem that I proved back in 2018, we get this result. There is S naught in between 0 and 1 such that omega S naught is not a unique gap ground state, for it's gapless or degenerate, or omega S shows a discontinuity at S naught. Okay, so this means that there is a phase transition in this interpolating model between 0 and 1. Okay, this is proved under this non-trivial assumption. Okay, in case the assumption is not valid, then if you look at the assumption, you find that then this omega 1 is not a unique gap ground state. So omega 1 is is singular or critical in certain sense. So this means that the existence of a phase transition in the ground state of this interpolating Hamiltonian has been proved without any assumptions. Okay, if the assumption is valid, then we have this. If the assumption is not valid, then omega 1 itself is critical. So we still have something strange in between 0 and 1. Okay, so this is what I said in the introductory part. Okay, so let me just briefly discuss the idea of the proof. So I will define the central object, which is called the twist operator, which was discussed by Bloch, Lieb, Schultz-Matthis, and Affleck-Lieb. First of all, I define twist angle for a given parameter alpha, and it's like this, but it's easier to look at this. So this theta is a function of j, lattice size, and it's 0, and then starts here, and it has a gradient alpha, and if it reaches 2 pi, then it stays at 2 pi. Okay, looks like this. And then I define the twist operator on finite chain like this, and this is simply the rotation about the z-axis, but the rotation angle is not uniform, but given by this or given by this. Okay. So it's a local twist operator. And when alpha is greater than 0, then you can take the limit where L goes to infinity in this, and what you get is this. Well, and I have to stress that you don't have to sum over infinite sites, because first of all, if theta is 0, then it's nothing. You don't have to do anything, add anything. And if theta is 2 pi, then since this is 1, again, you don't have to add anything. So you only have to add j, which is in this interval. Okay, so this is when, of course, alpha must be strictly positive, but in that case, this is a local operator on the infinite chain. Now I remark that in both the case, oh, actually, I have to put UL too. So U alpha and UL alpha are continuous in alpha. This is an important remark. Okay, so now I discussed the topological index defined by myself back in 2018. And I developed sort of general theory, but here I only concentrate on this interpolating Hamiltonian. So let's suppose that this is the ground state of this infinite chain Hamiltonian. Then this is a theorem. If this ground state is a locally unique gap ground state and is invariant under inversion, then the following index. This index is well defined. And also the index is invariant when S is varied, provided that omega S satisfies the above condition. So it means that if there's no phase transition, then this index remains the same. This is the index theorem. Okay. In order for the index to change, there must be some singularity in the ground state. That is what I proved. Okay, and if you look at this definition, it says that it's a alpha going to 0 limit of this quantity. But okay, so this is just the ground state expectation value of this unitary operator, twist operator, and divided by its absolute value. So this is simply the sign of the ground state expectation value of this twist operator. Okay, this idea goes back to Nakamura and Todo, and of course, the theorem says that you have well-defined limit, which is either 1 or minus 1. Okay. And as for the trivial model, this ground state is basically the simple tensor product of zeros. So this means that if you compute the ground state expectation value of the twist operator, it's very simple because you can just imagine that this is 0. And then, of course, you get 1. Okay, and then you get index 1. This is the simple case. The main theorem of this paper is that index, whoops, this is not int, this is int. Index omega 1 is minus 1. This is the main theorem. Okay, then this is what we do. Okay, let's set alpha to be 0. Okay, so since this is the definition, this doesn't make sense, but suppose this is minus infinity, this is infinity. So this means that when alpha equals 0, this theta j is constant, it's always pi. Okay, then you 0 of L. So this is the twist operator. It's defined like this, but it's simply this. So this is just a uniform rotation about uniform pi rotation about the z-axis. Now, let's recall from the basic elementary lemma that the ground state satisfies this. So in this ground state, this total SZ is 1. So this means that if you take the expectation value, you can simply replace this part by 1. So you get e to the minus I pi, that is minus 1. Very good. So we have proved that this expectation value, the ground state expectation value of the twist operator, and in this limit, you first let alpha goes to 0 and then make, then you can, of course, this is true for any L, so you can let L go to infinity. Very good. So you compare this with the definition of index, the index, okay? And it's the same expectation value and the same limit. Well, actually, if you're careful enough, you find the difference, okay? The order of the two limits are different. And of course, you know very well that you have to be very, very careful about the exchange of two limits, especially if you have like phase transition and things like that. And this is precisely the case. We have to be very careful. And so the exchange of limits are very, very delicate and non-trivial. And here is the main point of the theory. And we have to use this assumption on the existence of gap. And this assumption actually allows us to exchange the two limits. And I'm not going into detail, but this is a main lemma that I get from the assumption of the gap. The lemma says that when alpha is sufficiently small, this gamma is the gap, and when alpha is sufficiently small and L is sufficiently large, then this expectation value must live either in this interval or in this interval, okay? And then we know that when alpha equals 0, it's minus 1. So it's in this interval. And if you if you increase alpha within this interval, the continuity implies that you can never jump to this interval. So this is always in this interval. And this actually guarantees the exchange of limits. Okay. So that's the basic idea. And if you are interested in the proof, please take a look at the preprint. And actually, it's not long. It's very short. And the proof is elementary, and everything is written in this short preprint. OK, so here is the summary. There are two conjectures about the spin 1 antiferromagnetic Heisenberg chain with this Hamiltonian. Number 1 is the Haldane conjecture. It has a unique gap ground state. Number 2, it belongs to a non-trivial SPT phase, symmetry-protected topological phase. And we proved 2. But we had to assume number 1. And the proof makes use of the elementary index theory based on the twist operator, and it's very elementary. And of course, it is very, very desirable to prove also the conjecture 1. But it seems we need a new idea for this. OK, so that is all I wanted to say. Thank you very much for watching, and goodbye.